Okay, Chemistry 3202, Course Overview Review. Unit 2, Section 1, Lesson number 3. We're going to be looking at the relative strengths of acids and bases based on a table. This table can be found in the D2L content pages. On the main page, I have a link created called Tables, and you'll be able to link that there. You can also get this table, if you don't already have it, from the Department of Education Public Exam page. Just go to Chemistry and then scroll down, and you'll see the tables and charts there. Okay, this is dealt with on page 560 of your textbook. So here we go. This is what the table looks like if you have it, if you already have it. Now mine's a little bit fuzzy because obviously the table is pretty big, and trying to squeeze it down and to fit in the confined space, you lose a little bit of the resolution, but you get the idea. There's just certain aspects of this table that we're going to be looking at here. So you would follow along with a table that you have printed off. Okay, so here we go. Here are the outcomes for this lesson. Okay, we're looking at this particular reaction, this particular setup here, and we're saying, you know, last time we looked at the Bronsted-Lowry theory, and we said, you know, how do we know if something's going to be an acid or if something's going to be a base when we mix them together? And here's a good example. We can say, you know, what happens if we mix bicarbonate ion with hydrogen sulfate ion? You know, both of these can be an acid because they can both donate their hydrogens, and both of these can be bases because they can both accept the hydrogen. So how is each one going to behave when we mix them together? So that's what we're going to look at. We want to be able to look at our table and determine which one is going to be the stronger acid or strongest base accordingly. Okay. So we have to know the relative strength of each of these species. So we're looking at this and we're saying, okay, how do we know? What we have to do now is try and define what it means to be a strong acid or a weak acid, or better again, what it means to be a stronger acid or a weaker acid. All right, so let's have a look at it. Now before we do this, we're going to have a look at dissociation and ionization. So this is what we're looking at here. We're saying, okay, which one of these is going to donate their hydrogens? We're going to come back to this after we do the table. So we'll come right back to this page. Don't let me forget. So here we go. Okay, so the very first thing we want to do is get into a discussion about dissociation and ionization and whatnot. Now, dissociation from Chemistry 2202 and a little bit of Science 1206, this is what ionic compounds do when they're able to dissolve in water. All right, they dissociate or break into their ions. So a simple example of this is an idea that sodium chloride is an ionic compound. When it gets put in water, the water would pull it apart. So it pulls the ionic crystal lattice apart, and it separates it so that we have free-floating ions in the solution. So sodium ions are floating free of the chloride ion. So we're no longer in this ionic crystal lattice. Same thing is true for something like magnesium chloride. All right, that's an ionic compound. As soon as we put that in water, it's very highly soluble. As soon as it hits the water, it gets pulled apart into its respective ions. So magnesium ions and chloride ions. Okay, good enough. Now that's a physical process. That's a physical process, because if I wanted to get my sodium chloride solid back, all I'd have to do is evaporate the water. And as I start evaporating the water, of course, there's less and less room for the sodium and chloride ions. They start sticking together, and they would precipitate out and crystallize as a solid. All right, remember the dynamic equilibrium? There we go. Now, what acids are doing is a little bit different. Okay, acids actually chemically react with one another. And what happens is we're saying that ionization is when a neutral object gains a charge. So for our purposes, the ionization that happens is the reaction of, say, an acid with water to produce ions. So the neutral water is gaining a hydrogen ion, and it's going to be producing H3O+ or hydronium. The degree to which this chemical reaction occurs is going to be a function of how strong the acid is. The stronger the acid, the larger the degree of this chemical reaction. The weaker the acid, the lesser degree that this reaction would go. All right, so that's what we refer to as strong or weak. So Strong acids, by definition then, are going to be those acids that completely and utterly 100% ionize with water. So as soon as the HCl comes in contact with water, instantly every single last one of them would donate their hydrogens to the water. Every single last one of them would ionize. Okay, so every single HCl molecule is going to be involved in the chemical reaction. It's a single arrow. It's one direction. There ain't no going back for the most part. It's 100% in this direction. Whatever the concentration is of your acid, that's a strong acid, that's going to be the concentration of your H3O+. Big M refers to moles per liter. It's molarity. Okay, it's 100% forward. From an equilibrium perspective, if this reaction pushes forward, look at the way the arrow points. If we're pushing forward, the arrow is pointing in that direction. And we're saying that K is going to be enormous. It's going to be much greater than 1 because the equilibrium favors the products a great deal. A weak acid, by definition, is going to be any other acid that does not completely ionize with water. When the reaction is finished, there's a little bit of acid left over. And depending on how weak it is, there could be a lot of acid left over. Maybe the acid is so weak that it really doesn't want to react at all very much. So what we're saying then is anything that's less than 100% reacted or ionized is what we're going to classify as a weak acid. All right? So we can look at something like acetic acid, and we'll say, okay, this is going to be a weak acid. We know that because it's less than 50%. It's only like 45% wants to go forward. So when this particular acetic acid hits the water, it goes forward a little tiny bit. We get some ionization, but not very much. Look at the differences in their concentrations. For the strong acid, the concentration of H3O+ was equal, 1 molar and 1 molar. Look what happens for vinegar, acetic acid. We only get a very small fraction of the amount of vinegar that was put in the water. So in this particular weak acid situation, most of the acid would prefer not to react. So yeah, we got a whole bunch of acetic acid put in the bottle, but only a very small amount of it is going to go forward to produce H3O+. And we know that because if there's a lot of acetic acid remaining, that means the reactants are favored, and therefore K is less than 1, so reactants are favored. Now what does that mean for us from our table? Well, let's go look at our table and see if we can figure out what's going on here. If we look at our table, you notice that there's these acids above this line right here. These guys all have a percent reaction or percent ionization of 100%. So these guys here are known as the strong acids. Every single one of these guys has a percent ionization of 100%. And if you look at their K values, this is the K for the acid. Look, 10 to the plus 9, 10 to the plus 9, 10 to the plus 5, plus 3, plus 1. Every one of these guys has a very large K value. K is greater than 1, so it's going to push forward. All of these acids down here, this table is of course separated into acids and their conjugate bases. So these are the acids right here. All of these acids below this line are considered to be weak because look at the percent ionization, 51, 30. Remember, it's got to be 100 to be a strong acid. Anything less than 100, and it's going to be classified as weak. So there we go. That's the dividing line. So everything below that line is going to be considered a weak acid because it's less than 100% ionized. There we go. So hydrochloric acid, right there, 100% strong acid. Acetic acid, right there, they call it ethanoic acid. It's the same thing, right? Ethanoic acid is the same as acetic acid. There it is, 1%. So of every 100 acetic acid molecules that are put in the water, only 1.3 of them want to give up their hydrogens. The other 99 don't want to give it up, right? Very weak. There we go. So that's what we mean by a weak acid or a strong acid. Okay, so we want to be able to use this table then to try and just simply say, you know, of two acids, which is the weakest, which is the strongest. So here we go. We can use our acid-base table for that. And what we're looking at is that when two acids are combined, the highest one on the table is going to be the stronger acid. And when comparing bases, the lower one on the table is the strongest base. Let's go look at it. All right, remember now, I'm going to black out the base side. There we go. All right, that side's in blackout. You can see that on the West Coast only. There we go. So these guys are all the acids on the table. And if you look at the percent ionization, it's 100%, 100%, and all of a sudden it starts to drop down. And this is how they're ranked. They're ranked from the weakest acid. Water is a very weak acid. Weakest acid up to the strongest acid. So if I was comparing, say, vinegar, ethanoic acid, with the hydrogen sulfite ion, I know that vinegar is a stronger acid. It's not a strong acid. It's stronger than HSO3. All right, be very careful with that. It's only a strong acid if it's 100% ionized. Now, if we black out the acid side, what we notice on the base side is that the strongest bases, it's a flip-flop. Because on this side, this is the conjugate base of the hydrogen, the perchloric acid. This is the conjugate base of hydrogen iodide. This is the conjugate base of hydrochloric acid, CO-. These guys are weak bases. And as we start moving down, we get stronger and stronger and stronger as a base. And you look down here, OH- is one of the strongest bases known, like sodium hydroxide, very, very, very strong base. That's why it's used as Drano and things like that. So we can see that the table is flip-flopped. The strong acid is on the top. Strong acids are on the top, weak acids on the bottom. And if we look at the base side, the weak bases are on this side, the strong bases are down here. So I should write that in. These guys are weak bases. And this is the strong base down here. This guy is the weak acid. And this guy up here, these are the stronger acids. Unless you got 100% dissociation or ionization, sorry, and then you're going to be the strongest of all. All right, so let's have a look at some and see if we can follow our way through here. Oops, where are we going? Right here. Okay. This table is given to you on your public exam. The important thing is to know how to use it. That's the important thing. They give you a copy of the table. Make sure you know how to use it. So looking at this, we're looking at HClO and HF. So we go to our table and we say HClO and HF. There's HF right here in blue, and HClO, I have to search down through until I find it. There's HClO right there. Which is the strongest acid? HF, because it's higher. All right? So HF is the strongest. It's higher on the table. Okay, hydrogen sulfate, HSO4-, and benzoic acid, C6H5COOH. Let's go look at those guys now. So we go back to our table. Hydrogen sulfite, right there, and benzoic acid, right there. Look. Notice how they're giving us the names as well as the formulas. So benzoic acid is higher, so benzoic acid is stronger. Sulfite and carbonate, SO3 2-, and carbonate, CO3 2-. Now you notice that these guys are not acids, these guys are bases. So we're asking you now, which is the stronger base? Well, we got to go look at the bases here now. So carbonate ion, okay, where is that one on the table? Right there. And sulfite right there. Which is the stronger base? Well, in this case now, it's the lower one because we're talking about bases. So carbonate is a much stronger base. It's not a strong base. It's a stronger base than sulfite. So this guy here is stronger because it's lower on the base side. And finally, hydrogen borate, HBO3 2-, and hydrogen carbonate, HCO3 2-. Now, these guys can be acids or bases. So we want to look at these guys and say, which is the stronger acid? So let's go HBO3 and HCO3. So HBO3, now don't confuse here, look at that one right there. That guy's H2BO3. That's HBO3 right there. So, you know, that one's on the table a couple times. So there's hydrogen borate. And what about the hydrogen carbonate? And I'm looking at this, and there it is. There's hydrogen carbonate. So in terms of an acid, HCO3 is a stronger acid than this guy is higher. So it's a stronger acid. And now we want to look at these on the base side, because these guys are all amphoteric. These guys can exist on two sides. They can donate a hydrogen or they can accept a hydrogen. So if I'm looking at these guys on the hydrogen on the base side, we see bicarbonate is up there, and hydrogen borate. Again, watch out, I just picked H2BO3. Be careful, that one's on two sides as well. And there's HBO3 2- there. Which is the stronger base? The one that's lower now. So HBO3 is the stronger base. Okay, and these guys are amphoteric. They're found on two sides. There we go. So you got to watch that, right? Okay, so there's our acid-base table. Now let's go back to that question. I told you guys to remind me. Now let's go back to our question where we said, all right, we're going to look at this reaction where we're going to mix some sodium bicarbonate with some, say, potassium hydrogen sulfite. So we want to figure out, is the bicarbonate going to act as the acid, or is the hydrogen sulfite going to act as the acid? So we got to go back to our table here now. And I'm going to find these guys. Hydrogen carbonate is right there, and hydrogen sulfite is right there. So based on the positioning of these two ions in the table, both of them can be an acid, both of them can be a base, because I can find these guys on the base side as well. And just take my word for it, they're there. But the question is, which one is going to behave as the acid? We got two of them mixed together. One of them is going to donate a hydrogen. Which one is going to do it? Well, it's the one that's going to be the stronger of the two. So in this case, the hydrogen sulfite ion is going to be stronger. So in this case, the hydrogen sulfite is going to act as the acid, and this guy has to act as the base. And the reason it acts as the acid, because it's stronger of the two. Okay, there we go. So because that one's acting as the acid, now this is where the acid-base table comes in nice and handy here. Because the HSO3 is acting as an acid, look what happens here. I can show you what I'm going to get. I'm going to get that from my conjugate base. Because I'm going to donate that hydrogen there. I'm going to get rid of that hydrogen, and I'm going to get SO3 2- as my conjugate base, the sulfite ion. Look at that. So it tells me exactly what I'm going to get. So on the other side here, I'm going to get the sulfite ion. And of course, I'm going to get some H2CO3. So right off the bat, right from the table, I know that this is going to be my conjugate base, because these guys work together. This one and this one work together. Obvious, because of sulfite, right? And lo and behold, the other one there is going to be my conjugate acid. And obviously that these guys now are going to work together. There's my conjugate acid-base pairs. Okay, and there we go, and that's how we do it. So don't forget to go and print off a copy of that table. And very important table, we're going to use that again now in the next lesson. So With that in mind, make sure you're taking advantage of our online tutors, the online content, and if you have any questions on this, drop me a line in the discussions. All right, see ya.